Hello, welcome back. Just want to touch base with you and continuing what we were doing on light. In fact, at the top, just please write in lecture. Light 3A. It's a continuation of what we were doing, so let's go right into it. In this case, I want to be talking about scale because we talked about nanometers in terms of the width, if you will, of the wavelength of visible light. So let me do a little bit of a scale pause to make sure that I remind you about the metric system. So we're going to do a scale pause. Excuse me, scale pause. Just reminding you that the SI, the International System, the unit of length is the meter. Okay, so the unit of length is the meter. Okay, now having said that, I just want to put it in perspective. Sometimes we forget how this thing works. So if I end up doing like a scale of a decimeter, it's 1/10 of a meter. So I have a scale here of basically 1 decimeter. Okay, just like that. Okay, now that scale, it would be called 1 dm, 1 dm for a decimeter. On the right hand side, that's approximately 1/10, not approximately, but exactly 1/10 of a meter, which is 10 to the minus 1 meters. I want to make sure that we get and capture all of this. If I was to then draw 1 centimeter, just for scaling purposes, so we understand this is 1/10 of a meter, 1 centimeter would be like this approximately, if I'm doing my measuring right. That's 1 centimeter, 1 cm. Okay, now 1 centimeter is written as 0.01 meters, 1 centimeter, or 10 to the minus 2 meters. Are we okay with that? Now, if I go 1 millimeter, if I continue to scale this down, notice this is 1 decimeter, 1 centimeter, 1 millimeter. I can hardly even draw it. I mean, it's basically a very, very small measure like that. Maybe even that's too big. But that's 1 millimeter, 1 mm. So the scaling gets short very quickly. This is written as 0.001 meters, 1/1000th of a meter, or 10 to the minus 3 meters. Okay, does that make sense? So the next unit underneath that, if you will, if we scale by 3, is 1 micrometer, however you want to pronounce it, 1 micrometer, and this one would be 10 to the minus 6 meters. 10 to the minus 6 would be a 1 with 5 zeros in front of it, and a period, right? The decimal point. 1, 2, 3, 4, 5, 6, 10 to the 6 meters, so that would be in decimal. 1 nanometer, which is what we're interested in because we're talking about the wavelength of light, visible light at least anyway. 1 nanometer is 10 to the minus 9. 10 to the minus 9 meters. So that would mean a 1 with 8 zeros in front of it. Period. Okay, so there's a decimal point, 8 zeros and a 1. That will be 10 to the minus 9 meters. The last one I'm going to give you is 1 picometer, and that's 10 to the minus 12. Notice we're going up by 3. 10 to the minus 12 meters. So this would be 1 followed by 11 zeros in front. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there's 11 zeros before the 1. This would be in meters. So you should get the idea of how small these numbers are. Once we capture that, we realize that we are working in wavelengths of visible light in the 700 to 400 range or so of nanometers. Okay, so you know what you're talking about. Just also one additional thing I'll just add on to the scale, because we paused for the scale, is that 1 nanometer, okay, that when you talk about nanometers, I'm going to give you just some relative comparisons. So if you put an asterisk by it, approximately 2 nanometers is the DNA width. Approximately 40 to 50 nanometers is the yellow fever virus. And the last one is approximately 150 to 200 nanometers are small bacteria. So that should give you an idea in terms of how tiny those measurements are. Okay, now having said that, let's go through and look at light frequency. Now that we understand wavelength and how small they are, let's look at light frequency. So I'm going to go ahead and continue with light frequency. Light frequency. Okay. Frequency is actually the Greek letter nu. Looks like a V actually, but it's not a V. It's the letter nu. Okay, it's the frequency of light is basically how many cycles pass through a reference point per second. So it's measuring basically how many waves are going through a given second. So frequency of light wave is the number of wave cycles passing passing through a reference point in 1 second. Okay, the unit of frequency, is the hertz, abbreviated Hz. Okay, so if we were to give some examples, 1 hertz is equal to 1 complete cycle in 1 second. And I'll give you some examples. I'll give you 3 examples underneath. I'm going to try to draw this as best as I can. So let me do this in blue. So if I was to draw, I don't know, 1 second. Let me use a different ruler. So if I was to draw this, let's see, right there, 1 second. And I'll get you in sync in a second here. If I was to draw this and a wave that goes through it, so I'm going to try to draw a wave that comes up to a crest, comes down to a trough, comes back to a crest. Same thing, I'm going to go ahead and draw something from a crest, but before I do this one, I'm going to say that this is 1 second. Okay, the time from here to here is 1 second. So I basically have from here to here, from crest to crest, one wave has gone through in 1 second, one wave. So in 1 second, this would be 1 hertz. On the other hand, if I have 5 of them going through, so I'm not sure exactly how I'm going to divide this. 1, 2, 3, 4. Let's stop at 4. 1, 2, 3, 4. So I have 4. I was going to do 5, but that's okay. This will work as well. No, actually, I can correct that like that. So this would be 1, 2, 3, 4, 5. This one will be 5 waves have gone through crest to crest across, still in the given 1 second. So this one would be the 5 hertz frequency. Okay, now the next one I'm not going to be able to do, say exactly, but say there's 1,000 of them in here. Okay, so 1,000 waves are going through in the same given 1 second. Okay, I'm just going to do for something like that. Then I say from this point to this point, there is 1,000 waves that have gone through in that one given second, still 1 second. Then it would be 1,000 hertz. The frequency would be 1,000 hertz. You get the idea of how this is ended up working. Now, there's a couple of things I would like you to notice about this that leads us to a little bit of a deeper learning on this. Okay, you can always stop and go back to it. I'm going to go to the back and say, notice. Notice. As nu, the frequency increases, the wavelength, lambda, decreases. Okay, really important to know that as nu increases, lambda decreases. So if we were to draw a graph of this, something simple, and we can just sketch it, we don't have to use even a ruler for this. So as nu, the frequency increases, then lambda, the wavelength, decreases. That should be pretty obvious from the diagrams. That leads us to our understanding of the mathematical relationship where nu is inversely proportional to the wavelength. Okay, that's the principle in math that you need to know. Okay, so this becomes important. Now, having said that, we can do a couple of other things that are just really super cool. If you multiply the wavelength times the frequency, that gives you the constant speed of light. Okay, this is really key. Wavelength times frequency equals the speed of light. What that does is it derives for us, we can solve for wavelength and we can solve for frequency, so that gives us nu is equal to the speed of light divided by the wavelength, or the wavelength is equal to the speed of light divided by the frequency. Very important equations for our work. Okay, now on the side, of course, on this, okay, now I'm going to do a stop, think, and do, and then you can work through these problems. Stop, think, and do. Now that you got the lecture, you understood, hopefully understand the concepts associated with it, we can figure out some really easy problems. They're not hard. Do not be afraid of the arithmetic or anything like that. Very simple problems is, what is the frequency of radiation for a wavelength of 210 nanometers? What is the frequency of radiation that has a wavelength of 210 nanometers? Now, a suggestion on this is to please convert everything to meters. Nanometers to meters, the speed of light not in kilometers per second, but in meters per second. If you do that, all the math will work fine for you. So just as a word to the wise. Aside from that, everything should be straightforward in terms of using these two formulas to figure out the problems. Now, I'm going to give you three. The next one is, what is the frequency of a wavelength of 555 nanometers? And the last one, just kind of a little bit of the reverse, a little bit different. What is the wavelength of a frequency? What is the wavelength of EMR, electromagnetic radiation? So don't freak out over that initial, no big deal. What is the wavelength of EMR with a frequency of 4.95 times 10 to the 24 hertz. Okay, so I appreciate it. That's the end of basically lecture 3 on light. This is 3A because we took a break, but work through these problems and then you should be ready to do labs and do some problems. Thank you.